This video deals with antidifferentiation and is the first in a series looking at antidifferentiation. So for this one, we'll look at a couple of examples of antidifferentiation, but there's future videos to follow which will deal with this subject further. All right, let's have a look. The antiderivative of an expression like ax plus b to the power of n dx, okay, is 1 on a times n plus 1 times, in parentheses, ax plus b raised to the power of n plus 1, plus the constant of integration. There must always be a constant of integration. If we now differentiate this back, the constant disappears. N plus 1 is reduced by 1, so that comes down here and cancels with this n plus 1. And this becomes n up here, and then we go inside the parentheses to differentiate the expression there, and the derivative of that is just the constant a times the 1 on a out here cancels, and then we're just left with ax plus b to the power of n. All right, so that works that way. An exponential in the form e to the kx plus d, the powers or exponents here are k times x plus d. Antiderivative of that will be 1 on k times e to the kx plus d plus c. Again, if you differentiate that, the constant disappears on the end. This becomes e to the kx plus d times k. That k cancels the 1 on k, and we're back to where we started from again. If there are a constant out front, then the end result here would be multiplied by that same constant. The constant doesn't enter into the differentiation or antidifferentiation. It just multiplies throughout. All right, the integral 5x minus 2 to the power of 3, let's see an example of this first rule, will then be 1 over 3 plus 1 in parentheses times 5 underneath there. 5x minus 2 to the power of 3 plus 1, the power has increased by 1 plus c. 1 on 20, 5x minus 2 to the power of 4 plus a constant. If we were to the antiderivative of sine x dx will simply be cos x negative plus our constant of integration. So don't forget the negative. All right. All right. Oh, my messy handwriting. I shall just remove that and let me do it again. I will get it right. Okay, so what's antidifferentiate derivative? Sine x. Okay, will give us minus cos x plus a constant. All right. Now, let's see an example of sine 2 pi on 5 times x plus 1. Okay, the argument here in the parentheses, 2 pi x on 5 plus 1. We'll need here, this becomes our minus cos here of the argument, 2 pi x on 5 plus 1, but we need to also 1 over 2 pi on 5, because when we differentiate this again, derivative of cos will be minus sine. The two minuses will cancel, and then we differentiate what's inside the argument, and that gives us a constant 2 pi on 5 to multiply up front, and so that disappears, and we're back to just our sine 2 pi x on 5 plus 1. Tidying this up, we'll have minus 5 on 2 pi cos 2 pi x on 5 plus 1, plus our constant of integration. You must always write the constant of integration there, because when you differentiate, the constant disappears and brings you back to the original, but you must have it there because what you produce when you antidifferentiate is a family of functions, and that's why you need the constant on the infinite family of functions, because the constant could be anything. Okay, integral of e to the power of 3x minus 2, well, we could expand out the parentheses. That could be e to the 3x minus 6, so it's in this form of this second rule at the top here, and antidifferentiating that will give us 1 over 3 e to the power of 3x minus 2 in parentheses plus c. Now, this first rule here, this can have n can have fractional values as well. It doesn't have to be the integers. It can have rational values. So this square root 7x minus 2 is really the same as 7x minus 2 in parentheses to the power of a half. And we can antidifferentiate that. So it becomes 1 over 7 times, in parentheses, a half plus 1. The power is increased by 1, times 7x to the minus 2 to the power of a half plus 1, to give it 3 on 2 plus our constant. That gives us, tidying up, 2 on 21 times 7x minus 2 to the power of 3 on 2 plus c. All right, now let's have a look at this one. Rational functions again, one polynomial divided by another, and what we're going to do here is 5x plus 3 on x plus 4. We can simplify that with a bit of polynomial division. So 5x plus 3 divided by x plus 4, so 5x divided by x gives us 5 up the top here. And 5 times x is 5x. 5 times 4 is plus 20 there. Subtract the second line from the first. 5x minus 5x is 0. 3 minus 20 is minus 17. So the remainder is minus 17. All right. And what we have now is the quotient is 5 minus the remainder 17 over the divisor x plus 4. All right, now the integral of 5x plus 3 on x plus 4 dx is now the integral of 5 minus 17 on x plus 4 dx. Well, the antiderivative of 5 is 5x. The antiderivative of 17 over x plus 4 is 17 natural log x plus 4 plus a constant on the end there. There's a minus in the middle, don't forget. Okay. In general, the rule here is the integral of 1 on ax plus b dx is 1 on a natural log of ax plus b plus c. Okay. Now, how about we integrate between terminals, as often is the case, and we find the exact integral. So what we want here, the exact value, is the integral from 2 to 10 of this expression, 5x on 3 divided by x plus 4. Now, integrating that, we've seen that's 5x minus, antidifferentiating that, we've seen it's 5x minus 17 natural log x plus 4, evaluated at the two terminals, 10 and 2, substitute in the 10 here, subtract from that the substitution of the x equals 2 value in here, and what we're left with is approximately 25.6 by a calculator or some other package. And that is that.